Hey everybody. So what you're listening to now is the live episode we recorded in February in Seattle. And you might be wondering why it's taken me 6 months to upload it to the internet. Honestly, the state of the world has me alternatively bummed out, anxious, and furious. And work has been exhausting. Having fun with physics and friends seems, kind of rude. I've been worried about my physicist colleagues and friends who live all over the world. I've been worried about COVID numbers increasing exponentially and hurting or killing people. I've been worried about cops who seem to want the right to murder people in the street with no oversight or consequences. I've been worried about kids getting taken away from their parents. I've been worried about the rise of fascism. I've been worried about global warming. I've been worried about hurricanes and fires and smoke inhalation. I've been worried that the wave of unemployment and the people getting kicked out of their homes because they can't pay rent. And I've been worried about everybody's mental health because everyone is getting worn down with worry and isolation and loneliness and stress. But these feelings, even though they're hard to endure, not everything about having them is bad. We're worried because we love each other. Not just our friends and family, but people we meet at the grocery store or people we watch on the internet. And we're worried because we want to see everybody we see around us living safely and happily and comfortably. And we want everybody around us to stay healthy. In other words, these times are heavy because we're part of a community and we feel empathy with everybody around us in this world. As isolated as we feel, the proof of this feeling means that none of us are actually alone. No one person in the world could vanish away and not have the rest of us feel a loss. Even though it sure feels like a lot of people making the decisions these days sure want to pretend that that's not true. We're so exhausted. But we're exhausted because we suddenly all have so much important work that we find ourselves needing to do. And we recognize that everything we're doing and have been doing for years is actually really important. Teachers, students, parents, waiters, cleaners, cooks, cleaners, nurses, doctors, gas station attendants, everybody. We suddenly recognize how much we're being relied on. And we see how much we rely on a long list of other people, many of who aren't available these days. So yeah, it's been a hard year, but how much we depend on people around us has never been clearer. The quantity of people around us who are willing to make sacrifices for the well-being of complete strangers has never been more evident. So maybe we'll start hearing our politicians recognizing that our society isn't built around selfishness. It's built around taking care of each other and fulfilling our duties to each other. And maybe recognizing that we're all willing to endure hardships for the sake of a better, happier, healthier future means that we'll start doing something about the global greenhouse gas emissions and global poverty and all these other big problems that we've been ignoring. Because honestly, regardless of how 2020 ends, we're facing a lot of uncertainty in the future. But our hope has always been with each other. Like COVID. I mean, there are more scientists walking the earth today than ever before in history, and these biochemists and epidemiologists and virologists and doctors and mathematicians, they're all working on cures and vaccines and studies, and we can trust that they're all doing their best. But who was it that put them in those places? Who was it that trained them and built their schools and kept them fed while they were learning? We did. And the community of people who were save us from COVID were protected and supported all these years by a broader community, not just because we saw this day on the horizon. No, we did it because we love them, and supporting each other is what we do. The more we can see it, the more we know we can rely on it. And the more we know we can trust each other, the more trustworthy we become, and the safer, kinder, happier, healthier the future is going to become. Now, I know there's a lot of darkness out there these days. I'm feeling it, we're all feeling it, and there's lots of reasons to get frustrated with the people around us. But everything good in the future comes from us cooperating and supporting and building and defending and teaching and feeding and being kind and patient with each other. The more we do it, the better our future is going to be, together. Black Lives Matter, Indigenous Lives Matter, Trans Lives Matter. Don't vote for Donald Trump. I miss you, and I believe in you. I'm not going to charge the patrons for this particular episode because lots of people have it rough these days and it's worrying me. So if you want to withdraw your support for the show, that's fine. I believe you, I understand. You don't need to explain it, it's fine. I'm going to try to make some more episodes in the coming months, and I'll probably be charging the patrons for those. So if you want to get out, it's okay, because I still want to try to get to episode 100. Now, today's episode is really cool. We recorded in the before times, back in February in Seattle. Danica and Sarah do an amazing job explaining quantum computers. It was recorded on a live stage in a conference center in the middle of a conference center floor. It's totally bananas, so there's a little bit of ambient noise, which I thought was really neat, so I left it in. Also, you get to hear me sing and play my rad 8-string tenor ukulele, so have at it. And remember to keep science in your hearts. We're all in this together.
The beautiful city of Seattle, Washington, on the ancient and unceded ancestral lands of the Duwamish people, in the warm, rainy Pacific Northwest, home to the Space Needle and Washington State University and the nearby campus of the Microsoft Corporation. Where better for the American Association for the Advancement of Science to choose as the location of their 2020 meeting themed Envisioning Tomorrow's Earth. And so, scientists and policymakers from around the continent and around the world have gathered to speak about science and society and how the two interact with each other. And so, we too have come. The Titanium Physicist podcast has been invited to bring its wise and powerful physicists together to speak to the world about the science which will affect the world of tomorrow. It's my pleasure to visit this beautiful city, and it's my pleasure to speak to you today from the SciMike studio presented by This Study Shows, a Wiley podcast. And my name is Dr. Ben Tippett. And now, allez, physique! It's been a hard road, there's no turning back, and there's no end in sight to this darkening night, and that's a sad fact. I hear you come down for the graves in Kajila, for to walk through the stones and the names we have known, and there I'll meet ya. I'm laying out the table for to welcome you back home. I'm calling all the angels for to lighten up your load. I'm calling all the majors to end this general despair. From the graveyard and in Kajila in black clothing, I'll be there. Yeah. Maybe the best way to introduce this topic is to have a certain kind of puzzle in mind. You know those logic puzzles in newspapers? They go like this. 4 people are neighbors. Brent, Sarah, Matt, and Danica. Danica lives to the left of Brent. Matt doesn't have a green house. Sarah doesn't live next to Danica. Brent has a pool shaped like a bunny, etc., etc., etc. And then at the end of it they go, what order do they live on the street and what color are their houses? The thing about these puzzles is that the clues are all relational. They don't tell you anything directly, but instead they tell you how one person's information relates to another person's. And yet, there's always a single specific solution to the puzzles. Now, I want you to think about how these puzzles get solved. Newspapers even give you a grid to work with. Sometimes they're called grid puzzles, a grid of all the different possibilities, and then you're supposed to work with the relational clues one at a time, crossing out possibilities until you're left with the one solution. Now, doesn't all that crisscrossing of information kind of frustrate you? You can't just holistically put the pieces together and figure out the solution in one step. I always imagined when doing these puzzles that if I were only smart enough to hold all the clues in my head at once, I wouldn't need to slowly eliminate every possibility but the right one. You know, the popular Sudoku number puzzles are actually very similar in the nature of the information presented to you and the method that you solve them. Now, imagine using a computer to solve these Sudoku puzzles. There's only one way to arrange the numbers consistent with these clues, but the most common method of solving them using a computer is really just clever trial and error, quickly generating and searching through all of the wrong answers and letting the wrong answers shape your next guess. But essentially, they're randomly looking through wrong answers instead of using the relational clues to shape the properties of the right answers. I mean, even though you do not know whether Brent's house is blue or red, and you don't know whether Danica's house is blue or red, being told that their houses are different colors is still a useful clue which shapes the right answer. It's frustrating that solving these problems involves wading through all the wrong answers. And I'm saying all this because there is a type of computation which can retain the uncertainty in there, but also incorporate the relational clues as information at the same time. They can incorporate all of the clues together to figure out the answer without having to work around, mucking around with all the wrong false answers. It's a quantum computer, but how do they work? Today on the Titanium Physicist Podcast, we're going to talk about quantum computers and quantum logic gates. Behold, TIE fighters, from the SciMic stage at the floor of the Expo Hall at the 2020 AAAS annual meeting. This is the first live Titanium Physicists episode. Our special guests are old friends of the show, and they've generously agreed to come up from Portland and Burbank to join us today. The first from Lost Lander, his Aberdeen mixed media musical storytelling show is breaking hearts and changing minds. It's Matt Sheehy.
Hello, everybody. Thanks for having me on.
Nice. And second from the band Ramona Falls and Elvi. He's currently been working with... Oh, wait, this is live. I can't... He's apparently all the musical in the upcoming comedy musical cartoon Central Park. It's Brent Knopf.
Hey, Ben. Thanks for having us.
All right. So, my friends, two amazing titanium physicists have decided to cross international borders to help us today. Now arise, Dr. Danica Marsden.
Woo, woo.
Dr. Marsden is a physicist who did her undergraduate degree with me at UBC and then a PhD from the University of Pennsylvania. Afterwards, she was a postdoc at UC Santa Barbara where she did research on MKID detectors. And she also worked as a project manager for D-Wave Systems. Arise, Dr. Sarah Ejtamai.
Hi.
Oh, wait, here, hold on.
Hello.
No, you have to make a sound.
Oh, I see. Oh, beep.
Yeah, nice. Dr. Ejtamai got her master's and PhD from Simon Fraser University in British Columbia, Canada, and she's currently a senior experimental physicist at D-Wave Systems. All right, everybody, let's talk about quantum logic gates.
Okay, great. Well, maybe just to build up some intuition first, let's review regular computers, the ones that we know and love and use every day, or maybe spend too much time looking at in our hands. So regular computers speak the language of zeros and ones, binary, and everything is built up off of this. So numbers get translated into zeros and ones. Colors can get translated into zeros and ones, and images. All the different pixels can be encoded as strings of zeros and ones. And then all the operations that we do on this information gets enacted through a series of logic that we do. So it might say, look at one of these bits, a binary digit, and say, if it's a 1, I'm going to turn it into a 0, and if it's a 0, I'm going to turn it into a 1. Or it might look at two of those digits and say, if they're the same, I'm going to output a 1, and if they're different, I'm going to output a 0. So as it happens, decades ago, we settled on the best sort of way of creating the zeros and ones from Lego building blocks, which are called transistors. So they are little switches on or off, and they create our zeros and ones. And everything's sort of built up off of that. So now we're going to kind of use that framework to translate to how quantum computers work and how they're different and how they're the same.
Okay, I don't know if you know much about quantum mechanics or not.
We know a little bit, just a tiny bit. Yeah.
Okay, so just the general term is quantum physics is the physics that explains what's happening in microscopic scales, like subatomic particles, like electrons, protons, and very small particles. And that's very different than what feel in a daily life, and is ruled by totally different rules. So we kind of don't understand it in terms that we don't have any intuition for it. So it is a little different than what we are used to. So let's say, for example, you're a musician, right? Do you play more than one musical instrument?
Yeah.
Okay. Let's say, so if we had a quantum version of you, and let's say you can play guitar and, I don't know, piano, and you're able to play both of these, right? But if you have a performance somewhere, right, you have to play either that or the other one. But the quantum version of you can play both of these at the same time. So you can see that is the thing that we call superposition in quantum mechanics. The same can hold when we want to make, a superposition of the two bits that Danica was mentioning, 0 and 1. So then we will have a qubit that can do simultaneously 0 and 1, like qubit version of you that can do, both the guitar and piano at the same time. So you can see that, if you had a band that had a few of these quantum musicians, you could do kind of more with that band compared to a normal band, right?
I'm imagining one of those old-timey musicians that has like a big kick drum on their chest and they've got like a crash cymbal on their foot and they're like playing a trumpet at the same time.
Yes, but they could play different songs at the same time. So that is the...
But what does my audience see? Does the audience see me playing both instruments at the same time?
Okay, that's where the problem comes with all the quantum mechanics systems. So as soon as you start to have an audience or a recorder or anything, the quantum system, which is very sensitive, decides that it's going to go into either of those cases. So although, we have lots of power that can come with quantum computers because of this parallelism that exists, but then when it comes to the point that we want to measure and find what is the result of our computation, then the measurement problems comes into the story. So, but that's not the end of the story. So what happens is the quantum computers, we say they are good, as Ben was saying, when we want to explore different possibilities, because you can kind of engineer the interaction between qubits in a way that, it goes and kind of explores all the possibilities, but at the end, when you want to do the measurement, it has kind of found the best possibility that you want. So when you do the measurement, that wouldn't be a problem. Yeah.
The quantum mechanical you as a musician has stage fright, and you have to choose. So even though you were practicing both at the same time, as soon as somebody looks at you, you just do one. Just play the bass drum, Stars and Stripes Forever as fast as you can. Yeah.
And you choose that randomly. That's the problem.
Yeah. Okay. So let's review essentially what she said, because the aspects of this are superposition and measurement. Okay. Superposition is when your one object, can be in two states at the same time until it's measured, and then as soon as it measures, it chooses randomly one or the other. And the art and science of quantum mechanics is figuring out exactly what the probabilities of it being one or the other. Okay? So today we're going to be talking specifically about how we go about informing the system of all of the different clues that are in there, and we do it using quantum logic gates. And it's fun, but essentially the comparison needs to be made between classical computing and quantum computing, okay? So in classical computing, Danica said there are logic gates and it's all zeros and ones. Do you know why it's called a logic gate? It's a very Doctor Who name, right? It sounds like, oh yeah, I gotta put it through the logic gate. Logic gates come from formal symbolic logic, where you can do something called like a truth table. I don't know if you've ever taken a math class where they make you sort out the truth tables. It's essentially a way of comparing information and then summarizing it in a particular way. So there's three basic logic gates. There's one called AND, one called OR, and one called NOT, okay? So the NOT logic gate goes like this. You say one thing, and then the NOT gate says the opposite. So if you say a statement that's true, it will say a statement that's false. And this is a really useful way of relating things. Like, right, for instance, if you're describing Danica lives in the greenhouse, then Matt's house must not be green, right? Yeah? The and the or state logic gates combine two statements into a third statement. So the and statement says, it only says true if they're both true. So we'll say, Danica's in a greenhouse and Matt is in a greenhouse. If that's true, then the logic gate will say true. That statement is true. The and statement combining those two statements is true. An or statement in any other situation is false. If you're both not in greenhouses, it'll say false. If one of you is in a greenhouse and one of you isn't, it'll say false because they're not both true. The or statement works kind of like that. The or statement is true if either or both are true. So if Danica has a greenhouse, if the statement is Danica and Matt, Danica has a greenhouse or Matt has a greenhouse, the or statement will say that it's true if either of them or both of them have an or statement. Okay? So the and the or statements take two bits and turn them into a third bit, summarizing them. The and statement or the or statement. And that bit will be a 0 or a 1 representing whether the statement is true, the and statement or the or statement is true or false. Now, this is where things get really cool because any logical argument can be built out of a really complicated but potentially, not so weird combination of and, or, and not statements. And so you can make these, you can summarize, for instance, if Matt's house is green, then Danica's is not green. You can summarize that using a system of and or gates. And it's neat, and in varying complexity to the point where, you've got Facebook, which is a really complicated thing, and it knows that you like the Dukes of Hazzard, and it's like, oh, if this person likes the Dukes of Hazzard based on these interactions, then we'll sell them this advertising. All of that complicated information is actually being processed through a very elaborate cascade of and or gates. And it gets neater. So what we just said applies to logical statements, which is the fine art and science of true or false statements, saying if something is true or something is false. You can also do mathematics with it. So you can represent numbers using essentially zeros and ones in binary, right? Where the number 100 is the number 4, and the number 1001 is the number 9. Right, so that you can encode large numbers other than 1 and 0 in terms of a known chain of zeros and ones. And then you can use the logic gates, the and, or, and not gates in complicated ways to do multiplication, division, any mathematical operation just comes down to some really messy cascade of ands and or gates. If this one's 1 and then this one's 1 and then this other one's in 1, it's fun making them. But yeah.
That's amazing.
So the core of all computing is these three logic gates, and, or, not?
Yeah, it's the three logic gates in combination with the bits. So part of computing is encoding the information. If I'm spelling out somebody's name, if I'm spelling out Danica Marsden's name on my computer goes, okay, each of those letters corresponds to a certain string of zeros and ones. And then it will process those strings of zeros and ones as a piece of information. Or if I want to add two numbers, 7,205, times 6 million, those numbers will be encoded as zeros and ones. Or if I want to make a true-false statement, they're called Boolean operations. If I want to make a truth-false statement, it will encode that information as zeros and ones and then put it through the logic gates. So the logic gates and the encoding everything as zeros and ones is the basics for all classical computing.
Wow. So does quantum mechanics rely on the same three logic gates as well, or does it have different mechanisms at its core?
That's
slightly different. So, and this is where quantum computing becomes very powerful. Even though it seems at its core super simple and basic, instead of just 0 or just 1, you can have a combination in a qubit, a quantum bit, which is some part 0 and some part 1 at the same time. And when you, instead of stringing together a bunch of zeros and ones, you're stringing together a bunch of things that encode all of the in between, 0 and 1 and everything in between at the same time. And it means that you can kind of process multiple sort of possibilities or realities at the same time. And where this kind of really, to say it as simply as possible is that if you were trying to represent a typical quantum state that had 300 qubits, it would require more regular bits, just the regular zeros and ones, than the number of atoms in the visible universe to represent everything that's encoded in that state of 300 qubits. So you'd have to be able to faithfully describe all states and their evolution between measurements. And this just kind of shows that the quantum world is actually incredibly complex and rich, and it's probabilistic. So then, like having gates that operate on something that is a mixture of 0 and 1 becomes a little more complex and interesting. So I don't know if you want to...
There is, for example, one interesting thing happens when you use one of the superposition state in a kind of a gate that is called C0 gate. I will not go through the gate. It is a simple kind of operation. But what happens is when you have a superposition state in that gate, which you have the equivalent case in the classical computer too, something called an entangled state will be formed. So what's an entangled state? If I go back to that music analogy, right? If I have a quantum musician that can play these two instruments, and I have another quantum musician that I entangle them together. So I kind of make them kind of join and become one quantum system. But this kind of funny or interesting thing that happens is if you two travel anywhere across the world, you get separated, and then something happens that disturbs you and you decide that you don't want to be a quantum musician anymore, the other person will immediately know without any kind of communication that you are not quantum anymore and they won't be quantum anymore. So we have this kind of interesting, long existing correlation between quantum systems that is kind of independent how far apart they are. And that's one of the things, for example, really bothered Einstein because he was thinking, oh, this information should travel somehow. At least it should travel with the speed of light. But then the point is, no, there is no transfer of information. These two are one system, so they don't need to kind of communicate that way. So that's one of the interesting things, because we cannot copy information in a quantum computer, but making this kind of entangled state, that would allow us to, have different versions of them. But then if you disturb any of them, everybody is dead. So that's the problem with it.
Wow.
Is it difficult to keep them undisturbed? Is that...
Yes, larger they are, more of these qubits you have, it's easier to disturb them or bring some kind of noise into the system that will disturb them. Yeah, right. That's why. I'm sorry. That's why it is so hard to make quantum computers that have thousands, millions, or large number of qubits in the gate model case. Yeah.
So you've probably heard lots of companies are trying to build quantum computers. We've got Google and IBM and D-Wave, and there's Rigetti, which is another smaller company, Microsoft, and we haven't settled on what's going to be our transistor, equivalent of a transistor yet. So for making qubits, people have been trying different methods, from loops of superconducting wire, where the current can flow in one direction, and that would be like your 0, or the other direction would be the 1, more or less. Other people are trying to use systems of trapped atoms or ions, where the spin of an electron or a nucleus represents, if it's spin up, aligned with a field, that's a 0. If it's down, that's a 1, et cetera, and kind of build up off of that. But each of these types of qubits has its pros and cons, we'll say. And so some of it, the conundrum of building a quantum computer, why it's so hard, partly is that you really want these qubits to interact strongly with each other, so that they can have this entanglement and superposition, and you get all that power. But then you don't want them to interact with the environment, because that will sort of leak away information, and you'll lose that superposition and entanglement. Except then you need to be able to control them and measure them and do your gates and stuff. So the problem is you need essentially a perfect switch, and that's really hard to do. Say more about.
Yeah, that is the tricky part about it, because even to make these qubits to interact, that is considered some kind of noise, and even that will disturb the quantum quantumness of these qubits. So that's why it makes it very hard to scale these systems up. But do you have go
Oh,
ahead.
sorry. Yeah, I want. These live mics are kind of crunchy. Let's review what we just talked about because it's super cool. So, the deal is, we want qubits. Qubits have the power of being in more than one state at once. So it's not a 1 or a 0, it's both until we do an observation, okay? And quantum logic gates can do the same things that the regular logic gates can. There's a quantum equivalent of an OR gate, which switches zeros to ones, and quantum equivalents of the AND gates, etc.
Didn't you mean a NOT gate? Wouldn't that switch from 0 to 1?
What did I say?
These are OR gate.
Oh yeah, I meant NOT gate. We're live. Oh god, I can't edit that out. Okay, yeah, NOT gate. Thank you.
Okay.
Yeah, so there's quantum equivalents to all these things, but the gates can do more than just that. They can, what's it called? Quantum coupling. It's
Entanglement?
Entanglement. Oh man, I use editing as a crutch on this show so bad.
Well, so do we musicians when we make records.
Yeah. So the quantum gates can actually entangle two things. So you can say, okay, I don't know if this bit is up or down. It's a combination of the two. And I don't know if this other bit is up and down, but I know that these two bits are related. I know that if this one's up, then the other one has to be down. And if this one's down, then the other one has to be up. It's kind of like you and your friend can both play your two musical instruments at the same time, and you play different ones. So when you play the kazoo, your friend plays the drums, and if you play your trumpet, your friend plays the pipe organ or something like that. And the thing Sarah said was you bring them as far apart as you want. If you observe the system, if one of the friends gets observed and oh no, he's got to play the kazoo and only the kazoo, then the other friend, no matter how far away they are, will automatically start playing the pipe organ or whatever I said.
So entangled particles have opposite phase always, or can they have the same phase?
They can have the same thing. You can prepare them in different forms. They can have opposite, the same, or different combinations.
Okay.
Yeah.
So one of the powers of quantum computers, these logic gates, is that they can entangle two particles. They can describe that relationship. If you're up, then you also have to be up. If you're down, you also have to be down, even though there's no certainty about which one either is. And so it's kind of like those logic puzzles at the start. You can impart that information to the system, and solving the system, doing the computation involves, putting all that information together. The thing is, Sarah and Danica were both saying that it's really, really tricky. These systems, they can decohere really quickly. If they get too hot, in fact, quantum computers have to work really, really fast, because if they don't work fast enough, the qubits might get too warm, or a random photon from the universe will go and bump one and the other, and they'll collapse. And suddenly the whole system will collapse, and you won't have that nice entanglement and that nice superposition that you're depending on. So as lovely as this argument about how quantum gates work is, it's more difficult to implement than it sounds, because, one of the things you're trying to do is entangle two of these qubits, and if you're trying to entangle these qubits on paper, it's lovely. You just say, oh, you just entangle them, and then all your mathematician friends go, yes, that makes sense. But if you're trying to build one of these things, it's really hard to entangle them without collapsing the wave function, without getting an observation in and causing decoherence. And so you want the system to be in superposition stage, in entangled states for as long as possible, to do these long, elaborate, cascading series of NOT gates or logic gates, but you can't.
And so, do you know, do you see? Do you just get a wrong answer, or is there some red light that turns on that says, "Hey, emergency! All of your qubits just decohered, and you have to start over"? Or I'm sorry, maybe this is too soon to ask, but how does it? What are you seeing when you're actually running these problems?
So what happens is, for example, let's say that you have the qubit. That could be the superposition of 0 and 1, the same analogy as the musician, right? If you do the measurement all of a sudden, you will see, for example, only 0. You go back, you prepare the state again, you go and do the measurement, you will see only 1. And then you go back again and do that. And you do that over and over. And over time, you figure out, 50% of the time when I did the measurement, I saw 0, and 50% of the time did 1. But that's one side of the story, because it depends on the observer too. So if you change the way that you observe, you can totally get different answers. So we say that the answer that you get is kind of random and probabilistic. That's why it makes it hard and makes the whole thing to go poof away, because you're doing that, but then if your final result is totally probabilistic, then you wouldn't know what the good answer is. That's why you have to engineer and use the problems that kind of can get around this problem.
So one thing that for people who are constructing these qubits out of these different systems, whether that be, using photons. So, there are many ways that you can make a system that can be 0 and 1 at the same time. So one is using photons, polarized light. So it can be polarized sort of vertically or horizontally, or you can make a mixture. So the great thing about photons is they can be in coherence very well, but it's hard to make them interact with each other, and so that's one difficulty. But then also it's very hard to keep photons in one place, so you will lose photons very easily. Or with the case of the superconducting circuits, it's easier to make them interact with each other by using magnetic fields that will sort of essentially talk to each other. But then because they're talking to each other, there's information kind of leaking and noise. And so similar things. So with each type of qubit that people are trying to use, you have to go and you calibrate each type of qubit, and you look at how long can it maintain this entanglement and coherence. And so I think for some systems, which are very nice and isolated, which typically involve nuclear spins or atoms that are well isolated, their coherence might last as long as like an hour. But then for something like a superconducting circuit, it's on the order of 100 microseconds. So for each system, it's not like you can tell when you're running your experiments based on the measurements whether or not you're observing a system that maintained its sort of quantumness the whole time. But we also just are characterizing each of these systems well enough to know that if I am not doing my operation within whatever it is, 100 microseconds, then these things are not going to be quantum and entangled anymore.
Wow. If you could.
Well, okay, so I'm imagining like an oven where like the computation is happening inside the oven, and like what happens if you open the oven too early? Like, do you get an answer? Like, does the quantum system like answer your problem and then leave it somewhere so that you could open the oven anytime, or if you wait too long, then it decoheres and the answer's gone? Like,
no. Sarah was saying that. So in your souffle example, so the deal is you're doing these calculations because you don't know the answer, and that's part of the thing. So you'll open it and it will give you an answer, but you don't know if that's right or wrong. So then you'll run it again and it will give you a different answer. But the system's kind of probabilistic, so there's a chance that either might be right. And so you run it again and it will give you the first answer again, and then it will give you a second answer again. So it's giving you answers, they're just not the right one. And then you can figure out, because you're just getting noise out the other side, but you have to run it a lot to figure out that you've gotten noise. But once you figure out that you've gotten noise, it's because your system isn't properly isolated. I'm saying that next to people who actually work on these things. But yeah, it's because your system is losing coherence. It's decohering before the calculation is finishing. Is that right?
Yes, and then your final answer is always a classical answer. When you do the measurement, it's a classical answer. So what you want to do is you want to make the quantum computer to kind of find that classical answer for you. So if you find the classical answer, it has already, decohered, so it doesn't matter when you go and you find it, that's what you're looking for.
So, sorry, I'm a little confused. So you said the final answer is classical, but there is a probability associated with that final answer?
No,
as
that's
well?
what we like to do. We like to reduce the probability to probability of one of having the right answer. That's what you want to do.
In an ideal case, you would sort of initialize your system with the problem that you want to solve, and then you would, close it away in the oven, the very dark, very cold oven, and you'd walk away for a while, and you would let it do its thing, and it would use quantum mechanics to do the calculation, and then you would make sure that you didn't come back too soon. But inside of there, it would do the calculation, and then it would get to an end result and be classical. And then sitting there waiting for you when you get back is this classical answer. If you do come back too early and open the oven door, you're going to force it into, giving you a classical answer, and that snapshot, it may not be done. It may not have finished the calculation process. So you may have prematurely opened the door and forced it to give you an answer which isn't the full calculation.
It's like Jell-O instead of a souffle, I guess.
Yeah, are all quantum computers necessarily cold?
No.
Okay.
No, it depends how you are implementing your system. For example, if you have a superconducting case, you will have these special fridges that keeps them very cold. But for example, in the case of atoms, if you have a trapped atom, you don't need to make them cold. Or in the case of trapped ions, which is an atom which has lost an electron. So in the case of trapped ions, you can keep these systems in room temperature. But what you would do is there's a very neat technique called laser cooling. So you would use lasers and shine lasers on these single atoms that you have contained in a place, and then kind of make them cool them down individually. So you don't need to cool down the whole environment that they are in. You go after each atom separately and cool them down. But then the cooling is one of the cases, because you want it to be cool. In the cases of atoms, what is really important is to keep them in a very, very low pressure, because any kind of little, even hydrogen atoms that are wandering around, they can come collide with these ions and then cause problems with them. So pressure is there. You want to have all sorts of fields that can interact with these systems very low. For example, in the case of superconducting cases, we have very, very strong magnetic field shields around it to make sure, there is no kind of magnetic field that's going around will affect these qubits. So it is always under very, very extreme environment cases that we can make sure that this quantumness persist, but then we're still not where we want to be. They are still getting bothered by whatever minimum kind of things that we have around them.
And will quantum computers forever be the kind of thing that exists at a separate central location where you kind of do cloud quantum computing, or will there eventually be a quantum computer, like a personal computer that you could have on your desk or in your phone?
I mean, it's hard to predict the future. I'm not sure that the original makers of computers ever foresaw Facebook, but the applications that we would use typically, or that would be used commercially, are not usually what people are going to need computers for in their day-to-day lives. So it's hard to imagine right now something that the average person would be doing on their laptop. But even then, right now you can access a couple of companies' quantum computers through the cloud online for free, actually. So that's probably the paradigm that we'll wind up in, is that if you really need access to a quantum computer, you access it through the cloud. Maybe for certain government security, it would be an issue, so they would have their own physical system on hand. But yeah, so we're kind of in this era where companies have managed to put together sort of 50 to 100 qubits that can be coherent enough and entangled for long enough that you can get about 1,000 operations in, gate operations, before the signal to noise just gets too low. And so now we're kind of, we have this imperfect control over these qubits. It's called the noisy intermediate scale quantum computing era. And it's like you have this Swiss Army knife is like your penultimate quantum computer, it can do everything, but right now all you have is something that has like the little scissors, and you're trying to figure out what it's good at, and so you're like, okay, well maybe I can cut some paper with it. So as much as we may have heard all this hype about quantum computing, right now we're at a scale where it's not that ultimate quantum computer, and we're sort of exploring different algorithms that might be useful, that might provide some sort of commercial advantage to companies.
How does 1,000 operations compare to like some other application that I might use a classical computer for? Like, is that a pretty powerful, like, is that like doing a calculator computation, or is it like?
So right now, like, some of the applications that they think might be the most fruitful are things that are sort of inherently quantum to begin with, and that you're simulating a bunch of particles, which are quantum mechanical objects, or looking at maybe trying to design novel materials. So how can you make solar cells more efficient, creating new materials for that. Drug discovery.
Yeah, like protein foldings and different kind of proteins that you can form. So I want to emphasize here, as Danica said, first of all, we are not picturing to have a cell phone that's totally quantum, because quantum computers, even mathematically, they're good to do certain things, but they are not good for everything. So they do certain things much better than a classical computer, but that doesn't mean that they are doing everything better. So the future will probably be a combination of classical computers and quantum computers. But the point is, so far, like historically when it started, we knew how computers work. So it kind of made sense to kind of expand that model, that circuit model, gate model, to kind of design the computers that we want. But that's not the only way to do it. As a matter of fact, where I or Danica were working, they're doing completely different sort of operation for these quantum systems. It's something called quantum annealing. So we are not using a gate model. Instead, we're using quantum annealing. That means that we are going to be able to do certain things very easily, but we can't do everything that a gate model can do at the state that we have our computers now. But even the noisy, very small-sized, computers, qubit computers that other places have, they can't do everything that we want that dream machine to do either. So it makes sense to kind of go and see, okay, what is my system capable of, and what kind of application I can do with this system with these capabilities. Mm-hmm. So I can tell you a little bit how quantum annealing, for example, works.
Please.
Yeah.
Feels like a plot twist.
Okay, yeah. So since I've been sticking to this music analogy, maybe I still can use that. So imagine that you're very good at playing one kind of song. So you know everything about it very, very well, and you can do that very easily without thinking. It just comes trivial to you. But then there is something else, another song that's very complicated for you to play, and you have never played it and you don't know how to do it. So if I give you the notes for that simple song and very slowly change the notes to that more complex song, then you will find yourself playing that more complex song. So that's what we do for this quantum annealing. We start with a problem that we know how to solve very well, and then very, very slowly we change the system to guide it into a problem that we want to find the answer to. And then if you do that slowly enough, then you will be found the best answer that you want. So.
Right, yeah. So, I mean, I guess just as there are different ways to build qubits, we have discovered that there is more than one way to do the quantum computing itself. There's the gate model using the logic gates, which was inspired by the classical computers, but then there's quantum annealing, and there are even other ones. There's one called measurement-based quantum computing. And so, as Sarah said, with quantum annealing, you would take your algorithm. And D-Wave actually has more qubits than the 100 we said before. It's about 2,000 qubits right now that are available for that style of quantum computing. And so instead of using the quantum logic gates to execute your quantum circuit, you're using adiabatic quantum annealing. And in that process, you have to encode your problem. So say you want to optimize a portfolio of financial investments over all of the possible ones you could choose. So you need to encode that into the way that the qubits are laid out. You might need to represent one of your variables with many qubits kind of together as a logical qubit. And then you set that problem as sort of weights and couplings between the qubits. And you start out, as she said, with kind of having a quantum fluctuation part that is at first higher, and then you kind of turn that volume down through the computation. And you're starting out with this ground state and a ground state that you know, and then as you proceed through the computation, you kind of turn up the volume on the problem that you've encoded, and you're hoping that if you go slow enough and you keep things isolated enough, that you'll sort of slip into the ground state of the problem that you're trying to solve. So that's sort of how annealing works. Yeah, and then, I mean, D-Wave, for example, has been looking at doing machine learning, for example. We've been able to recognize images like cars in images, or digits, processing digits in images. And people are trying to use it as a recommendation system. What hotel you might like to go stay at when you're traveling, for example. Yeah, so people are attempting to use these different types of quantum computers for real-world applications.
I'm sorry, I just imagined this like high-tech lab, and they're like, just like steam pipes and stuff, and they're like, we're about to get the answer, and you would like to stay at the Sheraton the best.
Exactly, because you like hot tubs.
Yeah, because you like hot tubs. Yeah.
The Sheraton doesn't have a hot tub. So let's review, because this is really cool. So we started the episode talking about quantum gates. Oh, I'm sorry. Yes, you're right. Hello. Cuddle up to the microphone. We started the episode talking about quantum gates, but the deal is that if you have quantum gates and you have lots and lots of bits, you're essentially doing something analogous to classical computing. You have a universal computer. This laptop can do anything, plus all the quantum applications. Absolutely fantastic. Unfortunately, we have technological limitations. We're not at the point where we can implement those ideas yet. So there are other frameworks for doing quantum computation that give you a specialized quantum computer. These quantum computers can only tackle specific problems, but they can still tackle the problems that you can't do classically. Because with a classical computer, you're pretty much limited to doing smart trial and error. Do it, see what works, it doesn't work, do it again. Work your way through the possibilities in a smart way until you find the answer. That type of computation, if you've got a really fast processor, that's great, but the more complicated those problems get, the longer it takes your processors to do, right? Yeah. And so classical computation is limited. Quantum computation's got all sorts of theoretical applications that classical computation can't do. So we're using these other frameworks to build really specific computers. These computers only do one thing, but they can do these things that classical computers can't.
Or
Or
they can do, but it takes them a long time to do. So it's impossible to do it with them, but it will take much longer to do it with them.
Is cryptography an example of that?
Quantum cryptography is another sort of applications of the quantum mechanics. We have been using quantum technology for many other applications. We've been talking about quantum sensors. Quantum computing is one of the applications, but for example, even the transistors that Danica mentioned, we understand how transistors work because we know quantum mechanics. Lasers, it's all working based on quantum mechanics. So we have been, applying these quantum mechanic rules to build up all these devices that we've been using. This is not the first time we're trying it out.
It's interesting that you bring that up, because there is I'll talk louder, closer to the mic. There's something called the Shor's factoring algorithm. And this is a very famous idea that we could use quantum cryptography we could use a quantum computer to break the way we are encoding information securely over the internet. So if you enter your Visa number to get a Sheraton room with your
This podcast is sponsored by Sheridan.
Yeah, I wish. No, it's sponsored by This Study Shows, a Wiley podcast. But so the idea is that your computer is encoding that information using it's a shared key encryption system. So essentially that system is based on factoring really, really large numbers. So the sending computer and the arriving computer both know what numbers these big numbers split into, but it would take another computer a tremendous amount of time to figure that out. And that's essentially, it's not impossible to break this method of encoding the information. It's just computationally very, very difficult. This is something that theoretically quantum computers can do. And so everybody's like, oh, wow, boy, as soon as Google gets it, Google will know everybody's Visa number, as if Google already doesn't know everybody's Visa number. If you go on Facebook and it's just like, what's your personality type? Enter your Visa number to find out, right? So,
Yeah, I mean, I don't know if you guys have heard this, but some people are worried that quantum computers will break the internet, right? That everything will become unencrypted and all data will be no longer secure. I mean, that will require those sort of penultimate computers that we talked about, which we think are ways off. It isn't going to be possible with the state of play now with these quantum annealers or with the NISQ era quantum computers that only have about 100 qubits that we're playing around with right now. But so the National Institute of Standards and Technology, a while ago, decades ago, has posed open competitions in the past to create secure hash functions and algorithms for security and encryption of information and data transfer. And some of those led to protocols that we use today. And likewise, in 2016, NIST launched another challenge for, trying to get ahead of when the penultimate quantum computers will come online. So people have already submitted in 2017, I think something like over 20 different ideas for how to keep things secure, data secure and encrypted, even in the era when the penultimate quantum computers come online. So people are thinking about this. We're trying to get ahead of it. We'll see what happens.
Yeah, but Danica, Sarah, can we use a D-wave currently on the market quantum computer to do Shor's algorithm and break the internet?
No, I thought I said no already.
Oh, maybe that's when I was getting the fruit.
Can we talk about Moore's Law real quick? So isn't Moore's Law, doesn't it have to do with transistors getting faster and cheaper a certain number of years? How does quantum computing play into that? Is it a parallel track? Is it just an extension of classical computing?
Moore's law is specifically about transistors, so it is not really a law. It is an observation that kind of motivated the industry to follow that. And what it is saying that every 2 years, the number of transistors that you have in your computer kind of doubles. So we've been doing that for a while. We've been just increasing the number of transistors. That means we were making our transistors smaller and smaller. But we have come to the point that we don't have much room to go any further. Like, for example, the iPhone transistors, their width is about 10 atoms. So you can see that we are not having much more room to go down. That's why
it's a fraction of the width of a hair.
Yes. So that's why the supercomputer centers that we have, it's becoming bigger and bigger because, the transistors, they can't go much smaller than what we're having. And that's one of the motivation that people like to think quantum computers are going to help in this era.
Yeah. One last question maybe. I don't know if we have more time for that, but is quantum computing is it mainly a use case of quantum physics, or is it also creating some discoveries in quantum physics? Like, is the use of it driving discoveries?
Yeah. You want to answer? Yes, for sure. Because one of the things is we can use these quantum computers to simulate different quantum computers. So it is really hard to simulate a quantum system with a classical computers because it doesn't have all the ingredients we need. And that's one of the biggest application of quantum computers because we use them to simulate all the other quantum systems, for example, figuring out how molecules work and, how do they interact with your body. And that's the whole drug discovery. That's why they're helpful. So they help you in discovering new ways of how quantum systems are working.
Mm-hmm. Yeah, I forget the size of molecule where it transitions from just not being possible to truly simulate a certain size of molecule with a classical computer basically at all. And yet, the building blocks of life are based on that. So yes, we will probably, through quantum simulation, using quantum computers, discover a lot about what's going on the smaller scales.
Yeah, well, one thing I really appreciate about quantum computing, just from the philosophical theoretical side, is that it's put a completely different spin on how we talk about what's going on. Because, honestly, as a theoretical physicist, I'm like, well, anything can happen, you got these wave functions and they're collapsing, but you have these people like Sarah who are working on it literally and depend on it staying coherent, and they can give you a better sense of it as a real object and something that we're interacting with in technology rather than just being, something anywhere, somewhere anything can happen. No, so it's a fascinating. The development of the technology is fascinating in terms of its philosophical implications. You don't talk about heaven the same way you talk about wagon wheels, and so quantum computing's put quantum physics in the things that live in your garage type of technology. Okay, well, so. Let's start wrapping up the show. Oh, wait, hold on. I usually say that and then edit myself out saying it. Do you have any more questions?
Okay, Google recently announced quantum supremacy. Was that just a marketing ploy? What does that even mean? Does it matter?
So the term quantum supremacy was defined by somebody named John Preskill, and it was meant to describe a calculation or any calculation that we think that a quantum computer could do that a classical computer couldn't. And so in this case, Google has used their, roughly 50 to 70 qubit systems to generate random numbers. And so we think that that's something that they've achieved that classical computers can't, but is it useful in sort of day-to-day commercial applications? That remains to be seen. I don't know if you want to add to that.
And then meanwhile, D-Wave has way more qubits that it's working on, right?
More qubits, but a different style of computing. So it's a little more constrained in the sense that you have to be able to pose your problem in the way that the landscape is constructed using those qubits.
And the whole way that the quantum annealing works, it makes it more robust towards noise. So that's why it allows D-Wave to have 2,000 qubits and more, but it makes it really hard to make a gate model, 50 or 100 qubit numbers. Yes.
Cool.
Well, that was wonderful. Thank you, Dr. Marsden. Thank you, Dr. Ejtemai. You've pleased me. Your efforts have borne fruit, and that fruit is sweet. Here is some fruit. Dr. Sarah Ejtemai, you get an apple.
Thank you.
You have to make munching noises.
Oh, I see.
You don't have to bite into the actual apple, though.
That's hard.
Okay. Dr. Danica Marsden, you get another apple. Oh, gross. It just disappeared. I'd like to thank my guests Matt Sheehy and Brent Knopf for coming all the way up here to the 2020 AAAS annual meeting in Seattle, Washington.
Thanks for having us.
Yeah, it was a blast. Thanks.
All right, thank you.
Great questions, guys.
Well,
Good answers.
What? No, they get the what's it called? The fruit of knowledge.
Yeah.
Did I? Yeah. It's beeping. What's that?
Too bad we couldn't play you out with like two instruments at the same time.
Right.
Wrap it all in.
Are you still recording?
And then one of us is doing
We are.
Sudoku.
Well, yeah.
Everybody solo.
Yeah. Well, that's good. Thank you.
Thank you.
Thank you,
That was
everybody.
awesome. You guys are amazing. Thanks.